We're going to review enols a bit. A lot of this you should have learned in Organic 1, so we're reviewing some things you hopefully already know. The first thing to bear in mind, which is something we talked about in the previous slide, is that every carbonyl with an alpha hydrogen has an enol tautomer. So what are tautomers? Keto-enol tautomers are constitutional isomers that exist in equilibrium. And you may remember when talking about this in Organic 1, you learned that in general, the keto form predominates. So to refresh your memory, let's review a reaction where you learned about enols in Organic 1, and that was with the hydration of alkynes. So you could take internal or terminal alkynes. In this case, with an internal alkyne, we can just use an acid catalyst and water. And this is a hydration reaction where water gets added across the pi bond. So the triple bond becomes a double bond. And the net is that we add an H to one carbon of the pi bond, an OH to the other carbon. And this gave us the enol because we have the alkene with the alcohol bonded to it. But then the enol would tautomerize to form the more stable carbonyl compound. So you may want to review your Organic 1 mechanism for this. So why does the keto usually predominate? Well, the carbon-oxygen double bond is stronger than the carbon-carbon double bond. So the carbon-carbon double bond is approximately 103 kcals per mole, while the carbon-oxygen double bond is approximately 172 kcals per mole. That bond strength drives this equilibrium to the keto isomer. So although this isn't the mechanism for this, the way you can think about drawing a tautomer is really fairly straightforward. We have our main carbon framework here, and all you really need to do is redraw that, erase the pi bond, and then convert the carbon OH into a carbon oxygen double bond, and that's how you would draw the tautomer for that. Let's say you have this unsymmetric ketone here. What you want to be able to do is look at this and say, well, where do I have alpha hydrogen? I have alpha hydrogen on this alpha carbon. I have an alpha hydrogen on this alpha carbon. We have two enolizable positions, meaning you can draw two enols from this. So if we use the alpha hydrogen in red, we're going to put the carbon-carbon double bond right here. So we'll say this is enol A. Or if we were to use the alpha proton on the carbon that's in blue, we would get what we'll call enol B. So again, in solution, these enols don't exist to a high percentage. The ketone form is going to be present in greater than 99%. There are, however, a few circumstances where the enol form does predominate. There's a couple of cases where the enol predominates. The first is in 1,3-dicarbonyl compounds. So something like this. Now this isn't an IUPAC numbering, this is just saying that the carbonyls are 3 atoms apart. So there's one at 1, one at 3. In this case, the equilibrium actually lies to the enol where the double bond is in the middle between the 2 carbonyls. And you could put the double bond between 1 and 2 or between 2 and 3 because this is symmetric. Let's just put it between 2 and 3. So in this case, at any given time, about 25% of the molecules will be in the full diketone form. 75% will be in this enol form. So why is that? There's 2 reasons. The first is conjugation. When we have the second carbonyl, the double bond of the enol is in conjugation with that carbonyl, so that helps. The second thing is intermolecular hydrogen bonding. So if I draw this out again, this time I'm going to draw the bond to the hydrogen like this. What will happen is the lone pair of this carbonyl can hydrogen bond with that hydrogen. And this 6-membered ring type system here with hydrogen bonding is quite stable. We do also have alpha carbons on the outside that are enolizable, but those don't give us the same stabilizing factors, so those only contribute a very small percentage of enol tautomer. It's mainly this here. The other case is one that you've seen quite a bit and maybe haven't thought about, and that's phenols. If you look at a phenol, what we actually have in the structure is an enol. And you can draw the keto tautomer for this. I'm going to draw a short arrow to the right. Here's a keto form. Well, the difference between these is that the enol is aromatic, the ketone is non-aromatic. And for that reason, the enol form is present in 99.9%. If you need to review, here's the reaction you learned in Organic 1 for the acid-catalyzed tautomerization of an enol. So here's the keto tautomer. The way this mechanism works is we have acid, and we have our double bond. The double bond reacts with the acid. We put the hydrogen on this carbon such that you get the positive charge on the carbon with the OH. That's the most important thing in this step. From here, we can draw a resonance structure and use the lone pair on this oxygen. I'll move that down. Giving us this resonance structure. And then to get to the product, just use a B for some base with a lone pair. We'll come and take that proton from the oxygen.